good morning. So, we'll start with this representation theory. I can give you, I'll put some notes that you can look at if you want. Of a course I taught before in CISA, so it's more or less going to follow exactly what I do. So this is representation theory of finite groups. So we start with a group G, and if you think of a group, you probably have seen groups in an abstract sense, and you can do a lot with that. But in practice, even if you try to compute something with a group, for example, if you use these programs like GAP or Magma, there are several ways in which a group can be given, and each one has its own flavor and its own computational issues. So this is related to what we're going to do, because you represent the group in terms of other things that are an abstract group, in terms of things that you are more familiar with. So there's two things that we going to consider. So if you have a group, you can represent it as permutations of a set. So X is a set, and Sx is the group of permutations from the set itself. So you can think of the group G, and this is image by this homomorphism, as a group of permutations of a set. Another way you can present it, which will be mostly what we're going to do, is a similar thing, but now acting on a vector space over some field K, and GLB are the linear maps in V to V that are invertible, so bijective. So here they're just bijective maps with no structure. Here we want the maps to be linear maps. So if you pick a basis, you will get matrices. So here you can enumerate X. So if you list your elements x1 to xn, you give them a label from 1 to n. So n is, so we have a finite set X. Then you can think of G as mapping to the usual notation Sn, the permutations of n things. And here, if you pick a basis for your base, so say V1 up to Vn, if n is a finite dimension, then this map you can identify with the n by n matrices, invertible matrices. So a group, you can associate to it in more than one way via a map that we call a representation. as a group of permutations or as a group of linear maps. And as I said, the course would be basically the study of these linear map representations for a finite group. So these we will call linear representations. And this will be called a permutational representation. So mostly we're going to consider the case where G is a finite group, X is a finite set, and V is a vector space of dimension n, and our field almost entirely would be something like the complex numbers. In any case, an algebraic closed field. Things become more complicated if you consider other fields or infinite sets and so on. If you change those conditions, things are more complicated. So this is a basic case, but it's sufficiently interesting to be worth studying. So another point of view, so now I'm going to mostly concentrate on this case 2 of linear maps. So another point of view which is alternative which is useful, but I won't use too much, is you consider the group ring associated to the group G and your field K, which consists of formal sums where the A's are elements of the field and G is just the element of, so this would be G of G, where A, G's are in K. So these are formal sums, and you multiply two of them.
Do we require that they are finitely non-zero?
Yeah, well now from now on G would be finite.
Okay.
Okay? So unless I say otherwise, G would be finite, the vector spaces will be finite dimension, and if I talk about actions and sets, the sets would be finite. Yeah, but otherwise you would have to do some assumption, have some assumption like that. So if you have two of these, and you want to multiply them, you just do it by following all the rules of a ring, and so the only thing you will need to know is how two elements of the group multiply, and you just multiply them in the group. So everything commutes, the scalars commute with their elements, and so what we see is that we need, let's call it G1 and G2. So you just collect together those products of elements in the group that multiply to G. You multiply everything together and collect terms that have the same, the product of the two indices is the same G, and that's the coefficients of G. So you can think of this as the formal definition of what product in this ring is, and is a bit of a tedious verification that this gives you actually an associative ring, and the element 1 has identity, and the element 1 is the sum consistent of 1, the 1 in the group, multiplied by the scalar 1. So this is non-commutative if the group G is non-commutative, but is the associative ring. And since V is a vector space, you know how to multiply scalars by a vector by a scalar. And if you have a representation, so we have a map rho from G to V. So we have a vector in V. We know what rho of G of V is some other vector. Rho of G is some linear map from B to V. And the typical thing we'll do is abuse notation and write maybe this as G dot V, where rho is kind of understood and otherwise it becomes a big mess to keep track of all the letters and the parentheses. And we also even just say GV. So this means the group G acting on the vector V, and what action we're thinking about, it's something that is should be clear from the context. If we're dealing with more than one representation, we have to write it down to make sure we don't get confused. But this is a standard abbreviation. And so if what I like to say is that if we have an element in the group ring, I can act on a vector by simply using distributivity and using the fact that it's a vector space. So G times V is some other vector in the vector space. A G times it is scaling that vector by the scalar AG and then summing. So this makes so here this thing is an associative ring with unity, non-commutative in general. And this makes V into a KG module. So left. We will use the convention, the usual convention that the actions are on the left, namely G and V. So if I have G1, G2 elements in the group and I multiply and I act on V, these things are maps. So first you do G2 and then you do G1. Yeah. And that's something that one has to keep track of. Sometimes it gets confusing, and if you write the wrong things, you will get the action, you may get the G2 acts second and makes things a bit confusing. I'll come back to that when we encounter it. I mean, I'm just thinking of these G's as if they were functions, and the convention is the functions you write first and then the argument second, right? Unless you have a Polish calculator in which you do it the other way around. You know what I'm talking about. You know the Polish notation. There are calculators that if you want to do 2 plus 3, you do 2, 3, and then plus. And it's called Polish notation, at least it was called that way when I was a kid. No, here we just follow the standard convention of how functions and arguments are written down. So this means that what we have is a KG module, and you can see that a KG module is just the same as a representation, because you have to, if you have a vector, if you have a set on which which is a KG module, first you know how to multiply by scalars, because K is a subring of KG. simply by taking a scalar A and taking it to A times 1, where 1 here means the element of the group. That's just the product of things of the form A times 1 is the usual product in K and the sum as well. So this is a map of rings. And so if you have a set on which you know how to act by kg elements, you know how to act by k elements, and that gives the set the structure of a vector space. And if I give you an element in the group G, you see it as just an element in K of G, where this sum consists of one term, G itself, and so you know how to act by G. So a finite dimensional, so let me just say a KG module is the same as a representation, a linear representation with coefficients in K. So this is just a formal thing, and we sometimes will use it to make things a little easier, but so you could also say that what we have is a special case of the theory of modules over a ring, a non-commutative ring, but it doesn't necessarily make it any easier. Some arguments become easier if you view it this way. So I'm not going to use this point of view too much. Okay. So if you have two representations, V1 and V2, we can just talk about a map between representations. Which means map, so I'm going to use row 1 to indicate the representation on the vector space V1 and row 2 on the vector space V2. So if I give you an element of my finite group, row 1 of G is some linear map from V1 to V1, and row 2 of G is some map from V2 and V2. A homomorphism of representations, phi, is a map that goes from V1 to V2 that makes this commutative. I mean, this is just a fancy way to say that if I let me write it with all the letters. If I have a vector V, V1, and I act by row 1 of G to V1, then that's the same as acting on the vector in the image vector by row 2. So another way to say this is that if I aggregate this like this, where here GV1 means act by the representation row 1, and here G of this means act by representation row 2, I'm basically just saying that this map is G linear. So the way that G acts is preserved by this map phi. So not every, in particular, has to be a linear map, but not every linear map will behave this way. It doesn't have to commute with the way that the G's act. Okay, and if if phi is a bijection, then, so this is a homomorphism of representations. So phi bijection will correspond to isomorphism of representations. And most of what we want to do is study representations up to isomorphism. So let me just say that here, let's say that what we have is that phi is G linear. This is the terminology that we might use. So just to jump ahead, what we're going to prove is if you give yourself a finite group, there's in fact finitely many isomorphism classes of representations, of irreducible representations. So all representations will be sum of irreducibles, we'll prove that, and those irreducibles are in fact finite in number. So in a certain sense, describing representations becomes a finite problem. And these finite representations, finite irreducible representations are, the entire information will be contained in something called the character table. I mean, I'm giving you in 2 sentences what will take a few weeks to do. And this entire character table information is then something you can just print and have in your desk and check and use depending on what group you have when you're dealing with a particular problem with that group. And in fact, since you, to some extent, you can reduce the problem to simple groups, it becomes something you can print in a book. So there's something called the Atlas of Finite Groups that contains all the information on the representations of simple groups. And depending on your librarian, maybe it's next to the Atlas of the World or in the right place in the group theory section. But you should check it out. It's quite an achievement to have produced this sort of data. Okay, but we'll get there very slowly. I just want to tell you more or less where we're heading, and hopefully also give you some idea as to why we care about doing something like this. I mean, I always say, I admit that when I would first learn about this idea of representations when I was an undergraduate, I thought it was a completely stupid idea. And I had no idea why, if you have a group, you have to then change it and see it as permutations or see it as matrices. But I was young and naive, and I eventually learned that there is something to this, and hopefully I'll convey that to you as well. So let's start with something very, very simple, but somewhat a little misleading in its simplicity. If we have a representation on a vector space V and n is the dimension, a standard name for this is the degree of the representation. So we'll abuse notation often, and this is kind of standard. A representation means a map from G to invertible linear transformations of the vector space. Sometimes we'll call the representation just V without mentioning the map rho. And somehow instead of dimension, the word for the dimension typically is called the degree. Yeah, so often, because we're interested in representations up to isomorphism, the actual map rho will not appear very much, or it won't be essential. Okay, so let's look at degree 1 representations. So here, what we have is maps from the group G to GL of a vector space of dimension 1. But a vector space of dimension 1, the invertible elements are just non-zero elements. And let's, from now on, I'm going to assume that K is a complex numbers. So what we have is simply G maps to C star. And this is a homomorphism. So representations of degree 1 are simply homomorphisms from G to C star. So one important thing that I maybe should say now, so what you will see is that this theory that we're discussing is basically a very souped up version of linear algebra. Linear algebra being the case where the group is trivial. There's no group to worry about. And as such, we'll see coming over and over again various things that you have seen in linear algebra. So let's make the following point. So from now on, as I said, G is finite, V is of finite dimension, the field is C. So this, if I choose basis in my vector space, is some complex matrix, invertible matrix of sign n by n. So what can I say about this matrix? What are its features?
It's just invertible matrix.
It's invertible, but it's not just invertible. There's a few other things that we can say about it. It cannot be a completely arbitrary invertible matrix.
Hermitian?
No, not yet anyway. So there's two things I'd like you to think about.
The image of identity is the identity map.
That's true. If G is 1, it has to go to the identity. It's rho is a homomorphism. Maybe I didn't stress that enough at the beginning. I want you to think about two things. What are the eigenvalues? And what is this Jordan form? So what can you tell me about the eigenvalues of this matrix?
Non-zero.
Certainly non-zero because it's invertible, yeah. What kind of, they're complex numbers.
They are.
Are they of modulus 1?
Maybe.
Conjugated. Back pairs conjugated.
Not necessarily. No, it's not necessarily a matrix whose eigenvalues come in complex conjugate pairs. What do we know
The
about
roots of unity,
and why is that?
because the group is finite and G to the n will map to.
So G is finite, therefore G the element G is a finite order. So little g to the order of G has to be the identity by somebody's theorem. So let's say G to some number n is equal to 1. But this means that rho of G to the n has to be rho of 1. This is a homomorphism. And rho of 1 has to be the identity matrix. Right? So if you have a matrix rho G whose nth power is the identity, the eigenvalues of rho G have to be numbers whose nth power is 1, are 1. So this implies that if rho is an eigenvalue of rho G, then lambda to the n has to be equal to 1. Okay? The eigenvalues of the power of a matrix are the power of the eigenvalues of the matrix. Yeah? Think of it, for example, rho of G could be put in a triangular form, and if you raise it to a power, the eigenvalues are on the diagonal, and the eigenvalues will get raised to that power. Is that clear to everyone? So this is something, so this is the kind of thing that we'll need to have fairly clear in our minds, the kind of results of linear algebra that we'll appeal to often. But there's a bit more. I mean, this tells us that the eigenvalues in particular, what Farshim was saying earlier, the eigenvalues have to have, in particular, have absolute value 1. Yeah? Because they're roots of unity. So this is an observation that will be useful. So it's much weaker, but still useful. So the eigenvalues are 1 in absolute value. And what can we say about its Jordan form?
What is the Jordan form?
What is the Jordan form? You didn't see that in algebra?
The composition in blocks.
You never saw the Jordan form?
I think I have seen maybe once, but I actually don't remember.
Okay, so maybe let me give you a very... Sorry?
The name is familiar, but I don't remember.
Okay. Sorry, I have to move real slow because I have a back pain problem. So if you see me be a bit robotic, it's not anything but my back. So you should read about this because I believe that one should not go around in the world of mathematics without having some working knowledge of what this is. Although, of course, if you talk to people who applied mathematics, this is somewhat useless, depending on what kind of mathematics you do. So let me try to explain. So we have a matrix. Let's call it A. It doesn't have to be invertible for this statement. It's just an n by n complex matrix. If you change bases on your vector space, you will be changing your matrix by a conjugation like this. For U, some invertible matrix, which is the matrix that does the change of bases. And the standard thing in linear algebra is that you would like to change bases so that the matrix A becomes as simplest as possible. And what Jordan form tells you is that there is a way to choose U.
Lots of identities?
No, I mean you have to have the eigenvalues. Those don't change by this procedure. The eigenvalues are preserved. This is a conjugate matrix. So what it Jordan form tells you is that for each eigenvalue there is a block. Well, there are several blocks. So it's a little hard to write. Let me try to do this. So you can write the matrix in block form. Which each block, called a Jordan block, consists of the diagonal element being the eigenvalue, and then ones. So a Jordan block of size 1 would just be lambda, a block of size 2 would look like this, a size 3 would look like this, and so on. And a matrix A can be seen up to an appropriate change of basis as a sum of blocks of this kind for each eigenvalue. So for each eigenvalue you have a series of blocks whose size depends on the matrix A, is an invariant of the matrix A up to conjugation. Okay? So this is the statement of a Jordan form, is the existence of such a basis. And this size of these blocks is uniquely determined by the matrix A. So just to be clear, you have to do this for each eigenvalue. Yeah? So for example, so this you must know what's the meaning of a matrix being diagonalizable?
The sum of dimensions of agent spaces are equal to the dimension of the space. Or agent vectors are linearly independent of. If you have n linearly independent agent vectors, so we can write them.
Yeah.
Or the change of basis that make conjugation that makes it diagonal.
A simpler way to say it, all of those things are equivalent, but from this point of view, a simple way to say is that there is a matrix U, a change of basis matrix, that will take A to something which is diagonal. Let me write as diagonal some eigenvalues lambda 1 to lambda n, which could be repeated. For example, the identity is the diagonal matrix with all ones. So from this point of view, diagonalizable means that all the Jordan blocks are size 1. Okay? So this is the same as saying all Jordan blocks are of size 1. So diagonalizable matrices are, for many purposes, much easier to deal with than otherwise. And what I was trying to say earlier is, if your matrix comes from an experiment, something that involves measuring, the measurements will have errors, and so your matrix is not really the matrix that you want, but some approximation to maybe the matrix you want. And it is a fact that if you perturb a little bit the entries of the matrix becomes diagonalizable. So there's always a nearby matrix that is diagonalizable. So from many points of view, people don't care about these Jordan blocks, because in practice, if you're thinking about engineering type problems or physics, you can more or less assume that your matrix is diagonalized.
Is every matrix have a Jordan form?
Yeah, every matrix has a Jordan form, a unique Jordan form. Unique up to reordering. The size of the blocks is uniquely determined, but for each eigenvalue. But this is if you're dealing with things that are a bit discrete. For example, if you're dealing with a field that say is a finite field or other context, then the Jordan form is really important and you have to deal with it. And that also has applications in real life, so it depends on what kind of applied mathematics you may be doing, whether you care or not care about this issue. Okay, so this is just a parenthesis. Now let's go back to our problem here. And can you tell me, well, now I can be more specific. In this specific situation, can you tell me what the Jordan form of rho G is? Yes, you can. Let's look at a one Jordan block. What happens if I take this to the power n?
We get n instead of 1.
And lambda to the n. So, what should I conclude? What am I supposed to get? Suppose my size of matrices is 2. And I get rho G is that Jordan block.
So it's just diagonal. In our case, it's diagonal, not.
The matrix has to be diagonalizable because if it has any block of size bigger than 1, you'll encounter something like this. The powers of this matrix are never equal to the identity. Yeah, because we are in characteristic 0. Because no matter what power you use, this entry here will always be non-zero unless you take the 0 power. And this change of basis, U inverse, doesn't affect the fact that a power of a matrix is identity or not. So the conclusion is, and this is a crucial thing to keep in mind, first of all, the eigenvalues of rho of G are roots of unity, that we discussed before. In fact, the roots of unity of order dividing, if needed, or dividing the order of G. In particular, they have absolute value 1, and 2, rho of G is diagonalizable. This is for one individual matrix, rho of G. It's certainly not going to be the case in general that all the matrices will be diagonalizable simultaneously. So each individual matrix, rho of G, can be diagonalized in some basis, but the basis you need for one rho of G may be different from the basis you need for another G. Okay.
So all the representations in C asterisk out of the trivial are equivalent?
No. No, we'll see exactly, here's where the crux of the matter is, that you can do something for an individual matrix, but you may not be able to do that for all of the matrices in your group at the same time.
Can we measure this by introducing a Lie structure in the matrices?
By using what?
Lie structure.
No, I don't think that plays much of a role. we're talking about a finite group, so there's not going to be much of a topology involved or differentiability involved. So let's go back to what we were saying is degree 1 representations. That kind of went into a tangent that we don't really going to use it right now. So this is the same as the homomorphism from G to C star. C star is abelian. And if I have a homomorphism from G to an abelian group, what can I say about it? How can you describe the maps from G to an abelian group? There's something called the Commutator Subgroup, yeah, and it's a normal subgroup, and any homomorphism to an abelian group factors through the quotient, because if I compute rho on a commutator, it will map to a commutator over here. The commutators over here are trivial because the group is abelian, and therefore every commutator G maps to 1, and therefore it goes through here. And this group, it's called A, is abelian because I killed all commutators. So maps from G to C star is the same as map from A to C star, and conversely. So hom of G to C star is in 1-to-1 correspondence with hom of A to C star. So describing the representations of dimension 1 is the same as describing the representations of dimension 1 for abelian groups. Yeah? Okay, so now let's consider that. So a group is abelian, and we are interested in representations of dimension 1. And here's an interesting thing, because it looks somewhat of a simple or almost trivial case, but it turns out to be quite important. So I'll spend a little time discussing it. From the point of view of what we're trying to do, it is a really very simple case, but still is quite an important one. So let's now focus on the following. So we have A is an abelian group, finite abelian group. And we're looking at maps from homomorphism from A to C star. Because we map to C star, this is actually a group. You can multiply pointwise and it will give you a group, and it's usually called a dual group. This is a group. It's a group because you map into something abelian, so if you have row 1 and row 2 belong to hom, then row 1 times row 2 is defined to be row 1 of G, row 2 of G, and this gives you a well-defined product. If you had here GLN for n bigger than 1, this will not give you a product. So this is something you should check.
So if we had G over,
Excuse me?
your last sentence.
So check in general. Hom from a group G to GLN of C is not a group with pointwise multiplication. Because of GLN not being commutative, when you try to find how to multiply, you find that the lack of commutativity will prevent you from having a well-defined group structure on this set. So this is just a set in general. Okay, but this dual group we can describe. If I give you a finite abelian group A, we can describe what a dual is. So what do we know about a dual?
Does it have the same order as A?
It has the same order as A, but it's more than that.
Isomorphic?
It's actually isomorphic to A, but in a non-canonical way. So this works a bit like vector spaces. A vector space has a dual, and if you're in finite dimension, the dual is isomorphic to the vector space, but not canonically. So the theorem is that A dual is isomorphic to A non-canonically. And as I'll say in just a bit, this looks like an innocent, and it will take us, we can write a proof in one sentence. It looks like a triviality, but it has a long, interesting history behind. And I'll discuss it in a second. So how do you prove such a thing? So what we're saying is that we can just find ways to give all homomorphisms from A to C star, and then as many as A.
Because A is a finite abelian group, we know that it is a product of groups, of finite groups, or Z, B, and Z.
So this is a direct sum. Let me write it this way. We don't need too much of a detail.
Yeah, and we take the generators
Where
of,
these guys are cyclic. Yeah, this is the fundamental theorem of something. Yeah.
So we take the generators and the homomorphism from A to C star.
Yeah, let's go slow. So you will agree with this. This you've seen in the algebra class, right? PID, Z is a PID, modules over PID. Now, I claim that because it's a direct sum, it's enough to prove the statement for each summand. Okay, so this is point 1, point 2, enough to prove for A cyclic. Because if it's true for A cyclic, then I can do this for the sum. So each homomorphism you only have to give is homomorphism from Ci to C star. So this is the direct sum of Ci to C star. So we just have to give homomorphism from each factor. And third, now we can say this. So A is cyclic, is generated by some sigma of some order. Order of sigma is the size of the group, let's say n. So how do I give homomorphism from A to C star? Well, all I have to do is tell you where sigma goes, because everything else then will follow. A homomorphism will tell you then where sigma squared, sigma cubed, and so on is. And thus, those are all the elements of A. And so I can send this anywhere.
So a root of n.
It has to go something that satisfies the unique relation, well, the relation that sigma satisfies, which is that its nth power is 1. So I can send this to any zeta n, or let me just say zeta, which is a number, a complex number whose power, nth power is 1. And I have n choices for those zetas, and n is the size of A, and that tells us that this is in fact a bijection. And you see now where the lack of canonicity comes from, because there's no way to make a preferred choice of an nth root of unity in a meaningful way. There's a choice involved in here.
But can't we say that we take a root of unity which, I mean, like, because the roots of unity in C, they can be associated to angles. So
yeah, but that is not really a very, you could do that, but it's not going to be a very good thing. Because, I mean, you can always conjugate. Yeah, I guess you could do that, but I think it would be somewhat artificial. It's not going to be very canonical. I mean, once you're doing algebraic operations, you will have to deal with the Galois group, and these angles will not be something that the Galois group will respect. Okay, so this looks, as I said, somewhat innocent. The proof boils down to understanding the cyclic case, but it is quite an important fact. So let's just spell out what this means. So let's consider U, the vector space of functions from A to C, just functions. So this is a vector space, C vector space, by pointwise addition of functions. Our chi's are a subset of U. This U is a vector space, and A dual is just a finite set. So this is just a subset. And what I claim, excuse me?
Is dense.
Well, everything is finite here. So I think what you have in mind is slightly different. A is a finite set. It's not going to be dense, but what you I think probably you're thinking of is that there is a basis of U. Okay, so what that means is that if you give me a function from A to C, then I could write that function as a unique linear combination with C chi's complex numbers of chi A. Okay, so this is uniquely. what is this? This is the finite analog of the Fourier series. If a group A was the integers, not quite what we're dealing with, but if we extended this ideas a bit, then the characters will be given by exponentials, and writing a function as a sum of exponentials is decomposing in its Fourier series. So we could just call this a Fourier series. There's a sum, finite sum. And let's see. Let's do this. To prove this, we can give U a Hermitian product. So we're dealing with complex numbers, so we're going to be doing this often. Instead of when we talk about Hermitian, I mean inner products, we'll think of complex. So I'll call them a Hermitian inner product. And this will be an anticipation of what we're going to do for an arbitrary group G. Simply, we define the inner product of U and V, two functions, as UA, VUA conjugate. So I'll try to be consistent, and the conjugates will go in the second coordinate in my products. I might divide by the size of A, though it doesn't really matter for the purpose of what we're doing. And so what I like to claim is that these guys are in fact an orthonormal basis with respect to this inner product. So if I prove that they're orthonormal, then they're linearly independent, and because of what we proved before, the number of elements of A dual is the same as the number of elements of A, because they're isomorphic groups, and the dimension of U is what? Is the order of A, because to give a function from A to C, all I have to do is give some value to each A. So I have 8 different ways, independent ways of doing that. So to prove this corollary, it would be enough to prove that these characters are orthonormal. The fact that they're evasive will follow because they're as many as the dimension. So how do we show that these are orthonormal? Okay, well, let's just take chi1 and chi2, two characters. I think I never used that word before. Homomorphisms from A to C star are called characters. And we'll see later that the word characters for a general group will mean something slightly different. So I want to compute the inner product of chi1 with chi2. So I sum over A. So what can I say about chi2 bar? is also a character. In fact, is which character?
The inverse.
Is the inverse, because as we argued in general, the values of this character, well, in this case, since we map into something of dimension 1, a 1 by 1 matrix, it's its own eigenvalue, and the eigenvalues are roots of unity. So chi2 bar is in fact chi2 inverse. So the sum is chi1, chi2 inverse of A, because this is by definition the product chi1 and chi2. So what I need to show is that the sum of chi of A with A is the size of A if chi is trivial, and is 0 if chi is not trivial. And that will prove it, because then if chi1 is equal to chi2, then it's the trivial character, and I will get a total sum of size of A, which will cancel and give me 1. And if they're different, then this will be a non-trivial character, and then according to this, I will get 0. Okay?
But obviously, if chi is 1, then we get summation of 1 8 times.
Exactly. So chi equals to 1 should be clear, because then we just have the sum of 1 8 times, and
So,
that's
and
the
also,
size.
if it is not 1, we have the inverse of. For every A, we have inverse. We have inverse of A.
Yeah, let's be careful. What if your group is Z mod 2?
So,
Sorry,
What if your group is Z mod 2?
which group?
A.
But
The inverse of every
it will
element.
also sum to 0, because A plus A, it will be 0 also.
Yeah, but your argument of inverse won't work in that case.
The sum of nth root of unities are 0. So for all A, there are n elements which map to roots of unity, which would be 0, and that happens for each one.
Yeah, okay. I think it may be a little messy to write that idea down.
Okay,
You have to do it sort of, maybe you have to do it for each cyclic one.
Okay, one other way is to multiply by chi of b for some b, and then sum, and the sum would range over all values again.
Yeah, I think that's a little more straightforward. So if chi is not equal to 1, then that means that there is a b such that chi of b is not equal to 1. Yeah? So if I look at the sum of chi of A and I multiply by chi of B, then this is the same as the sum of chi of A times B. Well, then I'm using multiplicative notation for the group A. It's an abelian group, but my operation is denoted with a dot. And A times B runs over the same whole group A, so this is the same. So we call this sum S. This is chi maybe. Then chi of B times S of chi is equal to S of chi again. And since chi of B was not equal to 1, then chi of B S would have to be 0. So we have this times that for chi of B not equal to 1. So this shows that two characters that are distinct are orthogonal with respect to this product, and the same character with itself has norm 1. So in fact, well, all I needed was orthogonal, but we scaled it right, and we get an orthonormal base. So this A hat is not just a basis, but in fact it's an orthonormal basis with its inner product. And so this is indeed very similar to Fourier transform. We can decompose every function on the set A as uniquely as a sum of characters. And in fact, because the basis was orthogonal, or orthonormal, so recall that we have U is a function, and what we proved is that we can write it uniquely as C chi times chi of A, where chi is in the dual. And because the basis is orthonormal, U times, let me make sure I get this right. Let's see, what do I want to do? I think this is right. This is C chi. So I can compute this Fourier coefficient by taking the inner product with U. Now, so let me just tell you a little bit of history behind this, which is, I think, illuminating. Let's consider A. Let's say A is cyclic of size capital N. Then chi, as we discussed, chi of A from say J goes from 0 to N minus 1. The characters are, we can index them by chi of J by saying that this goes to e to the 2 pi I J times A over N, making this isomorphism explicit. And so what we're saying is the function U of A is a function of A that is periodic modulo N, has, we call them C sub J now. And this is even closer to the Fourier transform, Fourier series. It's a clear finite analog of Fourier series. And from this point of view, seek J x to the J is some polynomial, say C of x. X now is a dummy variable, and what we're saying is that U of A is C of e to the 2 pi I A over N. So what we've done by convoluted way is to show that if we look at the nth roots of unity, so we have, say, so this would be n equals to 6, a function of the indices 1 through 0 through 5 modulo 6 can be uniquely given by a polynomial evaluated in these roots of unity. So it's the interpolation problem. Now, what I wanted to mention is that, so two things. People in the 1800s, or maybe even earlier, use this to find the orbit of things moving in the sky. So Gauss, in particular, was interested in describing the orbit of an asteroid called Pallas, And the asteroid, it does something cyclic. So you can think of it as the position can be described by a point in the circle. And what you do is you observe it at different times. So what you have is perhaps these 6 observations. So at this time, at this time, at this time, and you find where it is. So you have certain values, A0, A1, not A0, sorry, U0, U1, up to UN minus 1. And now you can use this polynomial, or this Fourier series, to give the value for a point that is not one of these. So you can say, okay, well, I can now use my polynomial and evaluate it there, and that should give me an approximation of where this thing should be in between. And so this is exactly what Gauss did, and other people before him. So Gauss used this to predict the position of an asteroid, some object moving out in the sky. Okay, so that already is interesting, but what is even more amazing somehow is that I think he had 12 observations, and he wanted to do this calculation faster than you would imagine. So according to this, if you have 12 observations, you'll have to do 12 sums in here to find each coefficient. So you have 12 sums, and you have to do that 12 times. So that's a lot of calculation. So he actually found a way to do this faster. So already in what is probably around 1805, he discovered what was later became known as the fast Fourier transform. Which only got its name and its sort of modern discovery in the 1960s. And this completely revolutionized dealing with data, because it made the number of operations go from n squared to something like n log n if you have n samples, and that's an incredible saving. That means that you can actually use this in practice. And this is what's now known as the fast Fourier transform, and it was sort of developed by the names here. I'll write it down. I think it's Kaki and something like this. The name. It's a famous paper which made, as I said, the use of these ideas practical. And even today, I mean, this has completely, as I said, revolutionized the dealing with signal processing. And even today, this is done, this type of ideas are used to compress images, because what you do is you have a bunch of data, you convert, you compute its Fourier series, or compute these coefficients, and what you do is you truncate and eliminate all the high frequencies. So you just keep in this sum those terms that have a small denominator in this exponent, and that, of course, gives you not the thing you started with, but it gives you something that is good enough. So that's a way to take a big amount of data and compress it into a much smaller thing, and still be something recognizable by, if it's an image, by humans looking at it. Anyway, I suddenly not an expert in any of this, but I thought at least I should mention how this all fits into the larger world. So, summarizing, then this already shows a little bit of the use of this representation theory, but from the point of view of representation theory, it's a very, very not trivial, but fairly simple case. And in a way, what we're going to do is each one of the things that we mentioned, more or less, try to carry it over for non-abelian groups. And we'll find various things need to be changed along the way. Okay, so that was dealing with representations of degree 1. Let's go back to permutation representations, because these appear quite often. I mean, and so even though we're going to deal with linear representations, these are the ones that maybe show up. So recall that that means that we have a group G and a map to permutations of a set X. And again, G is finite, X is finite. So out of this permutation representation, I'm going to associate a linear representation. And here's where we have to be a bit careful with left and right to get things right.
Sorry, what we did, the case for GL1 of C when G is abelian. What can we say when it's non-abelian?
Well, as I mentioned, it becomes a question about the abelian quotient. You divide G by its commutator. The maps to an abelian group don't see anything other than the quotient by the commutator. Right? I mean, I mentioned that if you map G to an abelian group, then it maps to G over the commutator subgroup, and G over a commutator subgroup is abelian. So the whole theory just boils down to abelian groups. So in other words, you're not going to see, if you have an enormous group, but the commutator subgroup is everything, for example, then this is trivial, and the dimension 1 theory will tell you nothing. So in a sense, that's exactly why we want to be able to do this for arbitrary dimensions. So there are groups G for which, for example, simple groups, the commutator subgroup has to be either everything or trivial, and trivial means that the group is Z1 PZ. And so the theory, one dimension, degree 1 theory is great for abelian groups, and that's all there is for abelian groups. But for general groups, it will typically be not very useful, not give you very much. Okay, so if we have a permutation representation, I'm going to associate to this a linear representation. Remember, that means something with matrices acting on a vector space. And here I'll do it slowly because there's potentially a place to get confused between right and left. So one way, what I find the simplest way, the most succinct way of doing this is to do the following. I'm going to define a vector space on which G acts. And my vector space would be the space of functions from X to C. Just functions, no structure. Well, except that I'll think of it as a vector space, so I'm allowed to add functions pointwise and scale them by scalars. Okay, and this is worth you pondering on, I'm going to define rho of G. So this will be a linear map on this vector space, so it will act on functions. So if I give you a function f, I have to tell you what new function do I get. And the new function will be this. It will be f of G inverse x. Okay? So x is an element of my set, and G acts on the set. So it makes sense to say what G inverse of x is whatever G inverse takes x to, moves the x's around. So this is meaningful, and f is a function of my set x, so this is certainly a well-defined thing. Now the thing that you should check on your own is that this is the right way to do it, in the sense that this is a left action. So what I mean is, what you should verify, it's a simple thing, but you should do it yourself to convince yourself that this is correct. That if I do this, I do first G2 and then I do G1, this is the same as rho of G1, G2 of F. As I said, it's a simple thing, but you should do it. Maybe not now, but you have 5 minutes, sit down and verify it. And if you don't put the inverse, this will come out backwards. So what we mean by left actions is that the elements in the group operate like functions, which we write on the left and the arguments on the right. Yeah. You can also talk about right actions, which will be using the sort of Paulian notation, where you say the value of f of x, you write it as xf. Okay, which is not what all of mankind has agreed to do. But it doesn't matter. You can use one or the other, but you have to make sure you know which one and stick and be consistent. Anyway, this is something you should verify. And now this defines for us an action of the group G on the vector space of functions. And this is what I want to call the associated linear representation to the permutation representation. So for example, a very simple example of this is that G acts on x equals G itself by left multiplication. Right? If you have an element of G, and now we have to use different notations, so let's say, maybe write x. So x is in G, but I think of it as an element of my set x, and G is in G, and I think of it as a group element. Gx is Gx. Yeah, is the product of G with x. So this is the action. This is the product in the group. So maybe I forgot to say here, what is the dimension of V? Well, as we were arguing before, here we have a finite set, and we look at a function from that finite set to C. So to give a function is to give a complex number for each element of the set, and these things are independent things. So this is the current magnitude of x. Yeah. So here x is size G, so we get a linear representation of dimension equal to the size of G.
Excuse me, but here the value of any element in X can be any complex number.
Yeah.
So it has infinitely many choices.
Yeah. It's a vector space. It's an infinite vector space, but it has finite dimension. Yeah.
Yeah, okay. I see.
So let's make this precise. So let's give ourselves a basis of V. Well, there's a clear basis, which is to take delta sub x. This is the function defined as 1 if x is equal to y, or y is equal to x, and 0 otherwise. So this is a basis. Any function f is a sum of ax delta x for x and x, for sum of ax and c, right? If you give me a function, it has a certain value ax at x, and then I can recover the function as a linear combination of the delta function. Or maybe, yeah. So ax is nothing but the value of f at x. So the thing to watch out here, let's see what happens if I now act by a group element. So G and G, I do G acted on an F evaluated at X. By definition, this was F of G inverse of X. So this is the sum of AX delta. Sorry, I'm getting my x's mixed up. Let's call this Y.
So it is a g minus 1x?
Right, so what is delta Y of G of inverse of X? This is 1 if Y is equal to X G inverse of X, and it's 0 otherwise. So this is going to be 0 most of the time, except when Y is equal to G inverse of X, or what is to say X is G of Y. This is the same as Y, G, Y is X. Well, doesn't matter. I mean, so what I get is that this function at X we're just going to get back what we had. That's not what I mean to say. I think it's what I was supposed to say. I'm going to rewrite this. I change variables here. And yeah, so sorry. I guess what I want to say first is that this is the same as G, Gy of X. Yeah. So let me just write it out. So G F G of a sum of A Y Y
Sorry, but
delta
why
Y.
doesn't it appear on the left hand side?
Sorry?
Why doesn't it appear on the left hand side?
It's here.
Yeah, but we are calculating GF of X. And
Yeah. So this is a parenthesis. This is just about this case. So let me write this like this. if I act on this function, this is the same as y in x, ay delta gy. Yeah? And this we can also write by changing variables as a, this has to be this times g inverse, so it's g inverse of y. So, for example, let me finish with this. Let's look at the group S3 of permutations of three things. It actually naturally acts on those three things. So, out of this permutation representation, we get a permutation of dimension 3, a linear representation of dimension 3, okay, so this I can write as ai I from 1 to 3 delta sub I. Or if you like, you can just write this as vectors a1, a2, a3. So if I give myself the cycle 1, 2, 3, what is sigma of A? So let's call this thing A.
A3, A2, A1.
Hmm?
A3, A2, A1.
No. I did it so that we have this clear. The impulse is to say that, but it's not that, in fact. The way we define it, sigma A is slightly different. So let me write it this way. We have sigma acted on A1 delta 1 plus A2 delta 2, A3 delta 3. You can think of deltas as being the standard basis, if you like. So now this is A1 sigma 1, A2 delta sigma 2, sigma 3. So this is A1, 2, 3, 1. Yeah, it acts on the indices of my basis vectors. And so this is A3, A1, A2. Okay, so this, as I said, this is it's not complicated, but it's confusing. So you should spend a little time trying to make sure that this is clear. And it's not super important in a sense, but it's important not to get confused, because otherwise things start to sort of become a bit of a mess. So this is a convention. We could have used a different convention, but this keeps the action to be a left action. If you do what you did, you won't get a left action. Okay? And that, at some point, might make things complicated to follow. All right? All right, so we'll stop here, but please do check this issue of left and right.